In the enterprise sector, large generative AI models have introduced a systemic liability: the mass exposure of proprietary training data. In 2023, Samsung recognized this threat and banned the internal use of generative AI tools to prevent critical source code from leaking into external models. Shortly after, Microsoft faced immense backlash over its Windows Recall AI tool, forcing a total recall of the feature due to severe data persistence vulnerabilities. This tension between local data control and external access has historical roots. In 2015, Apple refused the FBI's demands to bypass device-level encryption, setting a strict standard for hardware privacy. The modern enterprise dilemma is that relying on device-level storage is no longer a complete solution. Training massive, distributed AI models requires moving computation to the cloud, exposing the data to new vectors of attack. The industry proposed federated learning as a solution. The baseline premise is straightforward. Raw data remains strictly on local edge devices, and clients only share model parameter updates with a central server. However, machine learning engineers frequently and dangerously conflate this decentralized network topology with cryptographic security. This illustrates the federated learning topology. An edge device computes a local gradient vector from its private dataset and transmits it toward a central cloud aggregator. But the vulnerability exists in transit. A man in the middle can easily intercept this gradient mid-flight. An intercepted gradient is not random noise. It contains rich, mathematically extractable information that maps directly back to the original source data. Through inversion techniques, an attacker can reverse engineer this seemingly abstract gradient into the exact raw training data. A distributed network topology provides zero mathematical privacy guarantees against an adversary equipped to invert the gradient. We can understand a gradient leakage attack strictly as an inverse optimization problem. The attacker initiates the process by seeding a dummy input, usually Gaussian noise pixels, and inferring a dummy label by analyzing the gradient signs of the model's final layer. Using the known global model and this initialized dummy input, the attacker computes a simulated gradient. This equation defines the attacker's objective function. They use the L2 distance to measure the difference between their simulated dummy gradient and the intercepted target gradient. A second-order optimizer, such as LBFGS, iteratively updates the dummy input pixels to drive this L2 distance down. As the gradient distance approaches zero, the dummy input mathematically converges into the original private training instance. Because gradients are deterministic functions of their inputs, any unprotected gradient is essentially a compressed, reversible snapshot of the private data. To break the determinism of the gradient, the standard algorithmic defense is differentially private stochastic gradient descent, or DPSGD. This equation demonstrates the first mechanism of DPSGD. By clipping the L2 norm of individual gradients, the algorithm strictly bounds the influence of any single data point. The second mechanism involves injecting calibrated Gaussian noise proportional to that clipping threshold. This noise obscures the gradient. By introducing randomness, it successfully derails the LBFGS optimization loop used by the attacker. But DPSGD introduces a strict, unavoidable trade-off between privacy and utility. As the noise multiplier increases to secure a stronger privacy guarantee, the model's classification accuracy and overall utility strictly degrade. Algorithmic differential privacy forces engineers into a zero-sum compromise between protecting user data and deploying a highly accurate, useful model. The industry has attempted to bypass this utility trade-off using explicit regularization approaches, specifically proportional DPDSGD. Proportional DPDSGD abandons gradient clipping. Instead, it injects noise strictly proportional to the model parameters, which preserves high utility on complex architectures like ResNet 50 and vision transformers. While it preserves classification accuracy, it fatally fails as a defense against gradient leakage attacks. This is the explicit regularization function for proportional DPDSGD. The mathematically deterministic penalty relies directly on the input data, not random noise. Compared under a reconstruction attack, DPDSGD reduces output to static, while proportional DPDSGD leaks the original image with high fidelity. Because the penalty is deterministic, the attacker's optimizer simply learns to account for the regularization term, rendering the privacy guarantee completely invalid. If algorithmic noise destroys utility and explicit regularization fails security, the defense must move out of the math and into the hardware. This is the premise of confidential computing and secure enclaves. We see this in production implementations like Apple's private cloud compute and on Yuna's C-class platform running on AWS and Azure. In an enclave computing architecture, data is encrypted at the edge, transmitted and decrypted strictly inside a hardware-isolated memory space in the cloud. Because the hardware enclave physically protects the data in use, zero algorithmic noise needs to be injected into the training process. This preserves 100% of the model's utility. Hardware enclaves currently offer the only viable path to train high-utility machine learning models on sensitive data without exposing them to gradient inversion. To solve the inherent vulnerability of trusting a remote cloud server, these systems rely on the protocol of cryptographic remote attestation. Before data transmission, the edge device requests and verifies a cryptographic hash of the software stack inside the cloud enclave. Once verified, the client device encrypts the training data using an ephemeral public key tied specifically to that temporary enclave session. Because these keys are ephemeral, they are not persisted after a reboot. Even if the server is later compromised or subpoenaed, the data remains cryptographically locked. Cryptographic attestation effectively extends the physical security boundary of the local edge device all the way into the public cloud data center. Federated learning is merely a distributed data topology. Without additional intervention, it operates as an open attack vector. To protect private machine learning pipelines, architects must make a choice: accept the strict utility degradation of differential privacy, or invest in the physical infrastructure of confidential computing. In the age of generative AI, privacy can no longer be assumed by design. It must be rigorously proven, either by mathematics or by silicon.